Okay, so in this video, we want to look at an application of the result that we obtained in problem 23.6 part A. This is now part B. Now in part A, we did prove that arctan of x was equal to the following power series as long as x is strictly between -1 and 1. Well, this means that we can replace x in this equality by any expression or any real number. As long as it lies between -1 and 1, the equality is valid. So our objective here will be to find a way to express pi as an infinite series. So here's our starting point. Recall that tangent of pi over 6, tangent of course is sine over cosine. Sine of pi over 6 is 1/2. Cos of pi over 6 is √3 over 2. If you divide by a fraction, you multiply by the reciprocal, so 1/2 times 2 over √3. 2 over 2 cancels, and we're left with 1 over √3. Notice that 1 over √3, since √3 is larger than 1, is a number that is between -1 and 1. Now tan of pi over 6 is 1 over √3, so take the arctangent on both sides of this equality. So arctan of tan cancels, and so pi over 6 equals the arctangent of 1 over √3. And now we have our choice of substitution. If we let x now be 1 over √3, 1 over √3 is a positive number smaller than 1, again because √3 is larger than 1. So we can make the substitution, replacing x by 1 over √3, in the following equality. Let's do so. Simplify and isolate for pi. So on the left, as we've just showed, arctan of 1 over √3 is pi over 6. On the right, let's try and simplify this term. Everything else is already simplified. So we have here an even power. The square will cancel the square root of 3. But we have this leftover of plus 1, so let's split those two terms up as 1 over √3 to the 2n times the leftover of 1 over √3. Now in the following step, I will multiply each side of the equality by 6. I will also factor this constant multiple outside of the summation, so we have a 6 over √3. And if we split the exponents here, this is 1 over √3 squared, which is 1 over 3 to the n. 1 to the n is 1, so we have a leftover of 1 over 3 to the n. We can now simplify here the 6 over √3, right? 6 is 2 times 3. And 3 over √3, of course, is simply √3. So we get 2 times the square root of 3. So in the end, we have that pi equals to the simplified multiple of 2 √3 times this infinite alternating series. Mission accomplished. Now, if we want to get an intuitive feel for the series, we can of course expand it. So if we expand to the first 4 terms, so the 2 root 3 stays there as a constant multiple. When n is 0, the first term of our series, so this is 1 over 1, also 1, simply 1. Then when n is 1, this is now negative 1. 2 plus 1, 3 times 3, 9, so negative 1 over 9. When n is 2, this is now 1. 2 times 2, 4, plus 3, 5. 3 squared is 9. 5 times 9, 45. Let's do one more when n is 3. Negative 1 cubed is negative 1. Over 2 times 3, 6, plus 1, 7. 3 cubed is 27. 7 times 27, well 7 times 7, 49. 7 times 21, 40. So we have 189, and so forth. So we now have expressed pi as a constant multiple, 2 root 3, of this fairly straightforward convergent alternating series. So if you want to approximate pi, you can do so by approximating root 3 and by summing a sufficiently large number of terms of this alternating series. And again, as you sum more and more terms, and as you get a better approximation to root 3, you will get a better approximation to pi. And that's it.